Hello, this is Mrs. Sullivan. Today we're going to be working with section 3.7 on direct variation. You'll notice that there's no page number listed next to your notes today. It's because we diverted just a little bit from the way the book was describing things. But if you did want to follow along with your book, it is similar information and it would be on page 138 in your book if you were interested. We're going to talk about something called direct variation, which is a very fancy term. I know it's very fancy. The definition of direct variation is that it means that the ratio of one quantity to another is a constant or the same. You've already learned that proportional relationships have the same cross products, so you should remember what proportional means. So direct variation is just another way of saying proportional relationship. So just in case you didn't catch that, proportional and direct variation mean the exact same thing. So far, you've learned to identify proportional relationships from pairs of ratios. Remember, our favorite way to do this is cross products. You might like to use mental math, but I like to use the cross products. So if you look at this pair of ratios, look at our cross products. 3 times 20 makes 60. 4 times 15 also makes 60. So yes, these two are proportional. Over here, 3 times 9 is 27. 4 times 6 is 24. Okay, just a refresher. You guys did awesome with that stuff, so we're pretty certain that you're going to do awesome with this. In this lesson, you'll learn how to tell if a table, graph, and equation show direct variation or have a proportional relationship. So let's look at this first example, identifying direct variation from a table. So you might remember that in lesson 3.4, we set up proportions from a table. You can use that information to help you identify direct variation from a table. So here's our first example. One of Mrs. Trombley and I's favorite characters, our good friend Buffy. She's a student we had years ago. Very funny girl, Buffy. Buffy saves $10 per week. She's saving to get her hair extensions. So if she's saving $10 per week and she's just started saving, she's just made this decision, so after 0 weeks, Buffy has no money. After a week, how much would she have? You're right, $10. And then after 2 weeks, $20. Notice that all you're doing is adding $10 a week or taking the number of weeks multiplied by how much she's making. So she'd have $30 after 3 weeks and $40 after 4 weeks. So Buffy's twin brother Bifford, we like to call him Biff, he already has $50 in his bank account, and he's also going to then save $10 a week. So this is where Biff's situation is a little bit different than Buffy's. At 0 weeks, Buffy had 0 money, but Biff is starting out with this $50. So after 0 weeks, he's got 50 bucks. But is he getting $50 every week? No, he's getting $10 every week after that. So he starts with 50. After 1 week, we can add 10 more dollars. So 50 plus 10 is 60. And then just continue adding $10 a week after that. So $80, $90. All right. So let's say you were given these data tables and you were asked by your teacher, do these data tables show direct variation, which remember is another fancy word for proportional. So when you were given 2 ratios and asked to decide if they were proportional or not, most of you just picked cross products as your favorite method to be able to choose. So if we look at Buffy's data table, remember you guys were taught how to set up a proportion from a data table. So let's just kind of pretend we've got 1/10 and 2/20, and we want to decide if those two are proportional. We could use our cross products. What's 1 times 20? You're right, it's 20. What's 10 times 2? Again, 20. So it appears that Buffy's information represents a proportional relationship. But if you look at Biff's, what's 1 times 70? That's 70. Is 60 times 2 equal to 70? No, it's not. That's 120. So use what you know about cross products to determine from a data table whether or not a relationship is proportional or shows direct variation. So the first example, or the first reason for how we can identify from a data table would be that cross products are equal There's two other things that Mrs. Trombley and I would like you to notice about these. Look at the very first column of each of their data tables. Notice that when Buffy hadn't put in any work, she didn't earn any money. But for Biff, after 0 weeks of work, he already had $50. You can tell that a data table shows a proportional or direct variation relationship because when the X amount is 0, the Y amount will also be 0. When X is 0, Y is 0. One more thing that we would like you to notice, so I'm going to squeeze that in over here. If you look at Buffy's, remember when you were asked back in elementary school or sometime earlier this year, if we said, okay, give me a fraction that's equivalent to 1/10. Do you remember what you would do? Well, remember that you would take the top and bottom and multiply them by like the same number. So let's say I wanted to take 1/10 and double it. So I would double the numerator and get 2, and then I'd double the denominator and get 20. Or I could take the numerator and multiply it by 4 and get 4, and I could take my denominator and multiply it by 4 and get 40. But look at what would happen if you tried to do that with Biff's information. If I take the numerator 1 and double it, I get 2. But again, when I take 60 and double it, is that equal to 70? No, it's not. That would be 120. So if you can't double the numerator and the denominator and get an equivalent fraction, then those relationships are not showing direct variation. So the way I guess I'm going to word that is when X, squeeze that in over here, when X doubles or triples or quadruples or quintuples, but I'm not going to write all that. When X doubles, so does Y. And I suspect we might be needing to clarify that a little more for you tomorrow, and we will. But here's a couple of examples for us. So here we have two data tables. First thing I notice when I look at a data table, I always look to see when X is 0. So if you notice here, I don't see X is 0. I see Y is 0. One of the ways that we can determine if our data table shows direct variation is that X and Y will be 0 at the same time. And so you'll notice that here, they're not. So that's my first clue that this is not direct variation. Let's look at cross products. What's 1 times 2? Well, that makes 2. What's 0 times 2? Well, that makes 0. So our cross products are not equal. And then look see what happens when I double the X. Do I also double the Y? 0 times 2 is still 0. So that didn't work. So this is an example of a situation that is not direct variation. Look at the next example. First thing I notice, 0, 0. When X is 0, Y is 0, that's my first clue that this is direct variation. Look at your cross products. 0 times 1, 0 times 3. Or if you don't want to use the zeros, 3 times 2 is 6. 1 times 6 is 6. Also look and see what happens when I double my X. If I double X from 3 to 6, do I also double my Y? I did. 1 doubled makes 2. So here's an example of a situation that does show direct variation because it met all 3 of these requirements. And just by the way, if one of these doesn't work, none of them are going to work. All right, flip your paper over, and I forgot to mention that you might be needing a ruler for this next side. And you guys are going to be flipping back and forth because we're going to graph the information that we had from our data table from examples B and C and put them into a graph. So for example C, I'll zoom in really big here, if that helps. Is that better? Okay. All right, remember to graph we need a number from our x-axis first and then our y-axis. And I'm looking at example C's data table. You'll notice that the first ordered pair in example C is 1, 0. So that means I'm going to go over 1 and up 0. So I'm just going to put my dot right there. The next point was 2, 2. That's a tough one to mess up, even if you mix up your x's and your y's. Our next x is 3 and y is 4. So x is 3, y is 4. You'll notice they're falling into a straight line, which is a good thing. The last is 4, 6. So go to the right 4 and up 6. So I'm going to connect my dots because I don't like to just leave those dots hanging. So we have a straight line. Now we're going to graph example D. Our first ordered pair in example D was 0, 0. Our next ordered pair was 3, 1. So to the right 3 and up 1. 6, 2. To the right 6 and up 2. And the last point is 9, 3. Again, don't leave them hanging. Connect your dots. Alright, so we already know from our data tables which one shows direct variation and which one does not. But look at these two graphs. I suppose I should make them as similar as possible. What do you notice is different? First thing I notice is that this graph starts at 0, 0 right at the origin, and this one doesn't. It's kind of scooched over a little bit. So that's really one of the first things that you should notice about direct variation, is that the graph will go through the origin, which is the point 0, 0. We can call it the origin. So you should be able to spot direct variation on a graph from a mile away. If it goes through 0, 0, it's direct variation. If it doesn't, it's not. Oh, Mrs. Trombley's prompting me here. She's like, oh yeah, there's straight lines too. Well, they are. They will always be a straight line because these are all what we call linear relationships, because we're dealing with like $10 per hour, the same rate. It's a constant rate. So they all form straight lines. That's not what makes it direct variation. It has to be a straight line and go through 0, 0. So it's got to have both of those. All right. This one, probably going to be the trickiest. Maybe I'm wrong. We'll see. Okay, we're going to identify direct variation from an equation. So here we have our favorite student, Buffy. She earns or saves $7 a week, and Bifford is saving, he has $50 to start off with, and he's saving $10 a week. So we're going to use the variables x and y to complete our equations, and you'll remember that when we're graphing these, our dollar amount would always be on the y-axis, and our number of weeks would be along the x-axis. So if we were going to write an equation for how much money Buffy would have after any number of weeks, we're going to use this equation. Y, representing the number of dollars, is equal to, well, she makes $10 per week. So we know that we're going to use a 10, and we would use x to represent the number of weeks that she's worked. So if she worked 5 weeks, we would just say 10 times 5 is $50. So the dollar amount, or the y in this case, would be $50. So Biff is another story. His amount of money, he's making $10 a week as well. So you could start with that. He's definitely making $10 per week. Notice the word per. This is the one that's going to be attached to the x. This is his rate of pay, $10 per hour. But Biff has a little something extra. He's still got $50. What will we do with that? It's not $50 a week, so we don't want to multiply it by x. We're just kind of going to add that to what he's got. So we're going to represent that with just a plus 50. So look at these two equations. They look similar in that they both have a 10x. But remember, Biff's got that little something extra. He's got that extra $50. So how can we identify direct variation from an equation? Well, the one with direct variation doesn't have anything extra. There's nothing extra added on. One that does not have direct variation, like Biff's, because we recalled from his data table that he did not show direct variation. Whenever there's that little extra something added on, there's not direct variation. So a couple things I'm going to have you write here for how you can identify direct variation from an equation. Direct variation will not have anything extra added to the variable term, so the term that has the x with it. And these are all going to take the form, they're all going to look just like Buffy's equations. It's going to be y equals something times x, but that something might change depending on who we're talking about. So they're all going to have a y, and they're all going to have an x, but the thing that's going to change is what's being multiplied by x. Your book is going to use this thing, and we'll call it k. So they will all have this form, y equals k times x. So we've got some equations down here, and what we're being asked to do is determine whether or not they show direct variation. And remember, we're looking for them all to look like this, y equals something times x. Well, you might be able to look at these right off the bat and notice that there's some addition signs in some of these, but we have to be very concise and make sure that we solve it properly. What we want to do is get the y all by itself, just like we were solving an equation. We're going to get the y alone. What do we have to do in this particular case to get the y alone? We got to get rid of that 1. So what would I do? I would add a negative 1 to this side of the equation. So now y is all by itself, but then I have to also add a negative 1 to the other side. 2x and a negative 1 are not constant terms, so I would write it just like this. 2x plus a negative 1. Does that look like this? Does it look like, well, let me write it right here. Does it look like y equals something times x? Nope, because it's got a little something extra. So here's one that is not direct variation. All right, look at this next example. The y is not alone, it has a 1/2. I want to get rid of 1/2. Remember, to get rid of a half, we multiply by the reciprocal. By doing that on this side, I get to cross a bunch of stuff out, and that's fun. So y is all by itself. Over here, I'm going to multiply by 2 over 1, which is the reciprocal. Well, what's x times 2 over 1? That's just 2x. Does that look like this? Y equals something times x? Nothing extra added? Yes, it does. All right. Ooh. I don't know if you remember this. I'm going to give you a Starbucks tomorrow if you can tell me which of those algeblock pieces was the xy. It was my favorite piece, if that helps. Anywho, all right, we got to get y all by itself. In order to do that, we need to get rid of the x. You'll notice that x is stuck to the y. It's being multiplied. How do you get rid of multiplying? Divide. I'm going to divide by x, and that gets y alone. So I'm going to do the same thing over here. Divide by x. So I have this, and while there's no addition in the problem, does it look exactly like this? K could be a fraction, but that's not what we're getting at here. This is not direct variation. This is going to be our next section, so we'll get back to that later. But currently, it's not direct variation. Woo! Yikes, look at this one. All right, so I have y plus 5 equals x plus 1. All I need to do is get the x all by itself. So let's get rid of this 5. So add a negative 5. So now y is all by itself. So I have to add a negative 5 over here. So I have x and 1 and a negative 5. These two are like terms. When I combine them, they make 4. So over here I have y equals x plus 4. And that does not look like this because it's like Biff. It's got that little extra something special. So we say nope, not direct variation. I hope you enjoyed our show.